As a demo of the finite element method, I'm going to do a sim scale introduction using this example. So I have a solid model of a very, very simple heat sink with 6 fins. You'll see that the fins are actually somewhat wide as an aspect ratio. That'll help us do the meshing so that we don't have to focus so much on the meshing for this example. But I'm going to do that as an example. So we have a bunch of fins that'll have a heat transfer coefficient associated with the outsides of the fins. I'll talk about how we'll do that as we go. So although we are not going to model the fluid flow in this problem, what I will do is use a correlation for the heat transfer coefficient for flow over a flat plate. That'll give us a local heat transfer coefficient over each one of the fins. I will heat up the bottom of this heat sink using a pair of heaters that you'll see here. And what I'll do is I'm going to set this up so in principle what I'd like to do is create enough volumetric heat generation in these yellow heaters to generate what corresponds to 20 watts on the first square or on the first heater and 30, I think I said 35 watts on the back heater. So this pairs with a in-class project that we're doing. The size of each one of these, the solid model will be given to you, but the size of each one of these heating units corresponds to like a real part that is 19 by 19 millimeters by 0.1 inches thick. So that's 2.54 millimeters thick. So that's basically the problem setup. The rest of so for the fins, we'll have a pretty well-defined heat transfer coefficient. For the other surfaces, like these little filleted surfaces, we don't really have one. So we could either make up a heat transfer coefficient to correspond like something realistic that we think it could be, or we could just treat it as adiabatic for the purposes of doing our simulation. So I think what I'm going to do is I'm going to treat these surfaces as adiabatic. Anywhere that's not being heated on the bottom side, I'm going to treat as adiabatic. So there'll be no heat transfer through the bottom of this heat sink. And we're going to look to see what the temperature distribution is in these fins. So like the typical questions that you're interested in is, for example, what's the temperature distribution in the fins? And in particular, are the fins isothermal, meaning that like every bit of surface area that you added with the fins, is that effectively, like, are you basically just adding more surface area to get rid of heat? Or do you have dead spots where the temperature is equal to the temperature of the fluid that's rushing past? So in that case, you wouldn't be transferring any heat. So that's like the main question that we want to ask. But I guess more to the point, we're just interested in learning how to set up sim scale simulations. Now, one thing I will point out about this solid model that is kind of important to think about is that it's actually not a perfect solid model. So let me show you some imperfections here. If I really zoom in to the front of this model, I'll see that I didn't really exactly line up, let's say, the fins with where the fillet comes together. So there's a bit of a gap there that'll, unless we do something about it, will need to be filled with relatively tiny elements to match the geometry. And I think there's a similar issue on the back side here. So if you like look really close, you'll see that there's like a slight misalignment here between these two pieces. And if I if I measure that piece, let's take a measurement. So that distance is something like 0.02 millimeters. It's very small. So if we want the finite element method to actually create elements that follows the geometry, we would, in principle, need to use elements that are only 20 microns wide and in some regions of the model. I'm going to try and set up the model so that it doesn't do that, because those are sort of wasteful. Like, we don't really care about that. Similarly, there's some other like little gaps here. So like this is sort of, let me deselect some things here. So that's 0.7 millimeters, so 70 microns. And that other gap was and this gap's like 0.27 millimeters, so 270 microns. I think what we might actually want to catch what's going on in that gap, but the other gap's probably not. So when we set up our elements, we might ask the finite element solver to not put in elements so tiny. So I'm going to set a cutoff of like, let's say 100 microns for the smallest elements that it's going to try and put in. So we'll get to that as we go. Okay, so this is the model I'm going to give you. Of course, a smart modeler might try to clean up some of those geometric imperfections, but I think realistically, like most drawings that people create actually have some imperfections like this. So this is sort of a good example of dealing with that.